Hey friends, welcome to the YouTube channel All About Electronics. So in this video, we will learn about the BiCMOS logic gates. So in this video, we will see that what is BiCMOS logic, why it is used, and what are the advantages and disadvantages of this BiCMOS logic. And then after, we will see the circuit of the BiCMOS inverter and we will understand the working of it. And after that, we will also see the circuit of the BiCMOS logic gates like the NAND gate and the NOR gate. So this BiCMOS logic is the combination of the bipolar logic and the CMOS logic. So this bipolar logic consists of the BJTs while the CMOS logic consists of the MOS transistors. So first of all, let us understand why the BiCMOS logic is used and what are the advantages of this logic over the bipolar and the CMOS logic. So for that, first we need to understand the limitations of the CMOS logic. So in the earlier video, we have already seen the CMOS logic gates and we have seen that the CMOS logic gates consist of the pull-up network and the pull-down network. So this pull-up network consists of the PMOS transistors while the pull-down network consists of the NMOS transistors. And depending on the input, at any given time, only one network is on. So in the CMOS logic gates, the static power consumption is almost zero. So that is one of the advantage of the CMOS logic. Moreover, it also offers the high input impedance and the noise margin of the CMOS logic is also very high. That means the logic high is very close to VDD and the logic low is very close to 0 volt. Apart from that, this logic also offers the high packing density. That means in the same size, it is possible to fit more transistors. But the only disadvantage of this logic is that it cannot drive the high capacitive load. It means that if we drive the very large capacitive loads, then the propagation delay would be very large. And effectively, it will degrade the speed of the overall circuit or the system. So many times, the logic gates can see a very large capacitive load when they are driving the long wires on the chip, or sometimes when they are driving the off-chip printed circuit board traces where the parasitic capacitance is several hundred times larger than the parasitic capacitance of the driving gate itself. But in short, when the CMOS logic gates drive very large capacitive loads, then the propagation delay of the logic gate will increase. So that is one issue with the CMOS logic gates. That means it cannot drive the large capacitive loads. On the other hand, if we use the bipolar logic, then it can provide the large output currents, particularly whenever it is used in the emitter follower configuration. And the same thing we have also seen in the ECL logic. And the reason these BJTs can provide the large output current is due to their large transconductance. So as you know, this transconductance is the slope of the IC versus VBE curve. And in case of the BJT, since we have the exponential relationship between the IC and the VBE, so the BJTs have the large transconductance compared to the MOS transistors. But the disadvantage of the BJT is that its power consumption is more. So this BiCMOS logic is using the best of both bipolar as well as the CMOS logic. And it is particularly useful when we want to drive the large capacitive loads at the high frequency. So in this BiCMOS logic, to reduce the static power consumption and to implement the logic, the CMOS logic is used. And then after, to drive the large capacitive loads on the output side, this bipolar logic is used. So this BiCMOS logic is often used in the RF and the high frequency applications to implement the mixed signal logic. So such designs have both analog as well as the digital part. And apart from that, it is also used in the high-speed telecommunication. So the only drawback of this logic is that as it is combining both bipolar as well as the CMOS logic, so the fabrication steps increases. And therefore, the fabrication process of this logic is complex compared to the CMOS logic. And because of that, the cost of the fabrication also increases. And because of that, the scaling of this logic is also difficult. Therefore, currently it is used only in the very niche applications where the same performance cannot be achieved using the CMOS logic. So now, let us see the circuit of the BiCMOS inverter and let us understand the working of it. So in the BiCMOS logic, the transistors of the CMOS logic is driving the NPN transistors. Or to be precise, the output of each pull-up and the pull-down network in the CMOS logic is driving the NPN transistor. So in case of the inverter, in the pull-up network we have only PMOS transistor. So as you can see, the output of the PMOS transistor is driving the NPN transistor. That means the base of the NPN transistor Q1 is connected to the drain of the PMOS transistor, and the emitter of the Q1 acts as a output. And if we see the collector of the Q1, then that is connected to the VDD. Similarly, if we see the pull-down network, then the one end of the pull-down network is connected to the output side. That means here, the one end of the NMOS transistor or the drain of the NMOS transistor is connected to the output side, and the source terminal is connected to the base of the Q2. So if we see this NPN transistor Q2, then the collector terminal is connected to the output side, while the emitter is connected to the ground terminal. So as you can see over here, these bipolar junction transistors are driving the output while the logic is implemented using the CMOS logic. And therefore, the power consumption of this logic will be low. And here, since the initial logic is also implemented using the CMOS logic, so the input impedance of these gates will be higher. So now, let us understand the working of this BiCMOS inverter. So in this BiCMOS inverter, when the input is low or the logic 0, then the PMOS transistor will get turned on while the NMOS transistor will remain in the off condition. So here, this PMOS transistor will act as a short circuit while the NMOS transistor will act as a open circuit. And here, since the PMOS transistor acts as a short circuit, so the voltage at the base of the transistor Q1 will be close to VDD. And therefore, this Q1 will get turned on. On the other hand, since the base of the Q2 is not getting any driving voltage, so it will remain in the off condition. And in this condition, this output voltage is equal to VDD minus VB. And this output voltage can be considered as the logic high. That means whenever the input to this inverter is low, then the output is logic high. Similarly, let us see the working of the circuit when the input is high. So whenever the input is high, then the PMOS transistor will remain in the off condition. And in this condition, it will act as an open circuit for the Q1. Therefore, this Q1 will also remain in the off condition. On the other hand, when the input is high, then this NMOS transistor will get turned on, and therefore it will act as a short circuit. So now, whatever voltage or the charge that this load capacitor is holding, it will appear at the base of the Q2. So earlier, if the output voltage is high, then this logic high will appear at the base of the Q2. So therefore, this Q2 will get turned on and it will provide the discharging path for this capacitor. So in the on condition, the voltage between the base and the emitter of this transistor Q2 will be around 0.7 volt. That means in this condition, the output voltage cannot go below that. So we can say that when the input is high, at that time, this Vout is equal to VBE, and this output can be considered as the logic low. So as you can see, in this BiCMOS logic, the voltage swing has now been reduced, because now the logic high is equal to VDD minus VBE, while the logic low is equal to VBE. But in this way, this given BiCMOS circuit works as the inverter, and in this way, it can drive the very large capacitive loads which cannot be driven by the normal CMOS inverters. Now one more thing, if you observe over here, then these two transistors Q1 and Q2 always remains in the active region, because here, since the base and the collectors are tied together, so in the on condition of the transistor, the voltage between the collector and the emitter terminal will be same as the VBE. And since it is more than the 0.3 volt, which is the typical VC voltage in the saturation, so we can say that these transistors always remains in the active region. And because of that, these transistors can be turned on and off faster. Now in this design, the issue is that when the input goes from the low to high state, then this PMOS transistor will be turned off, while the NMOS transistor will be in the on condition. So in this case, if you see, then we have a no path to remove the base charge of this Q1. So because of that, this Q1 will turn off slowly, and due to that we will have the increase in the fall time, because now the output voltage will take the time to reach to the logic low. Similarly, when the input goes from the high to the low state, at that time this PMOS transistor will get turned on, and if we see the NMOS transistor, then it will go in the off state. So in this case also there is a no path to remove the base charge of the Q2, and therefore the output voltage will not rise to VDD immediately. That means effectively the rise time of the logic gate will increase. So this problem can be solved by connecting the resistor at the base of the transistor Q1 and the Q2. So now when the PMOS transistor is in the off condition, then the base charge of the Q1 can be removed through this resistor. Similarly, when the NMOS transistor Q1 goes to the off state, at that time the base charge of the Q2 can be removed through this resistor. And in this way, we are providing the path to remove the base charge. But when we are using the passive resistors, then there will be a static power dissipation in the circuit. For example, when the input is low, at that time this PMOS transistor will be in the on condition, and therefore it will act as a short circuit. So in this condition, through this transistor QP and the resistor R1, there is a direct path between the VDD and the ground terminal, and through this path we will have the static power dissipation. Moreover, when this NMOS and the PMOS transistors are in the on condition, at that time these resistors R1 and R2 will also take some of the drain currents of the QN and the QP, and hence effectively that will reduce the available output current of the logic gate. So instead of using the passive resistors, if we use the MOS transistors, then this issue can be resolved. So here, instead of the resistors, the two transistors QR1 and the QR2 is used. So as you can see, the gate of the QR1 is connected to the input node. So now, whenever the input is low, at that time, this PMOS transistor will act as a short circuit, and effectively this VDD will appear over here, and because of that this transistor QR2 will also get turned on, and in this way it will remove the base charge of this transistor Q2. Similarly, when the input is high, then this QP will remain in the off condition while the QN will get turned on, and therefore it will act as a short circuit. So here, now since input is high, so this QR1 will also get turned on, and in this way it will remove the base charge of the Q1. So in this way, instead of using the passive resistors, we can use the NMOS transistors to remove the base charge of the BJTs. Now the issue with this BiCMOS logic is that we have the reduced voltage swing, and effectively we have the reduced noise margin compared to the CMOS logic, because in this case when the output is high, at that time this Vout is equal to VDD minus VBE, and whenever this output is low, at that time this Vout is equal to VBE. So we can say that in case of the BiCMOS logic, we have the reduced voltage swing. But using some design modification, it is possible to get almost full voltage swing. So this circuit is often called the R circuit. So if you see this circuit, then it is similar to the earlier BiCMOS inverter circuit which we have seen with the passive resistors. But here, the one end of the resistor R1 is connected to the output node instead of the ground terminal, and this resistor R2 is connected between the base of the Q2 and the ground. So now, let us see how this circuit works and how it provides the full voltage swing. So whenever the input is low, then this PMOS transistor will get turned on, while if we see the NMOS transistor, then it will remain in the off condition. So here, the base charge of the transistor Q2 will be removed through this resistor. So here, as soon as the PMOS transistor goes in the on state, then the voltage at the base of the Q1 is equal to VDD. So therefore, this Q1 transistor will get turned on, and therefore it offers the lower resistance path and starts charging this capacitive load. So we know that when this transistor is in the on condition, then we will have this voltage drop VBE. That means here, the output cannot go beyond the VDD minus VBE. So as soon as the output voltage across the capacitive load reaches this VDD minus VBE, then this transistor Q1 will go in the off state. But now if you see, then we have the alternate path through this resistor. So after the Q1 goes in the off condition, then this capacitive load charges up to VDD voltage through this resistor R1. And in this way at the output, we will get the VDD. Similarly, when the input is high, then this NMOS transistor will get turned on, while the PMOS transistor will remain in the off condition. So in this case, the base charge of the Q1 will be removed through this resistor R1 and the R2. On the other hand, if you see, then the voltage across this capacitive load will appear at the base of the Q2. So therefore, this Q2 will get turned on and it will offer the lower resistance path for discharging this capacitor. That means initially, the capacitor will discharge through this transistor. But as we have seen, when the transistor is in the on condition, then the output voltage cannot go below the VBE. That means as soon as the output voltage reaches the VBE, then this transistor Q2 will get turned off. But now in this condition, we have the separate path through this resistor R2. That means this capacitor can be discharged through this resistor R2. And in this way, this load capacitor will discharge fully to the 0 volt. So we can say that this resistor R2 pulls down the output voltage to the 0 volt when this Q2 gets turned off. And similarly, this upper resistor pulls up the output voltage to the VDD when the Q1 goes in the off state. And in this way, using this circuit, it is possible to get the full voltage swing. So this is the circuit of the BiCMOS inverter. But similarly, it is also possible to implement the other logic gates. For example, this is the circuit of the BiCMOS 2-input NAND gate. So as you can see, the only change that comes is in the implementation of the CMOS logic. So we know that in the CMOS NAND gate implementation, in the pull-down network, the two NMOS transistors are connected in the series connection. While if we see the pull-up network, then in the pull-up network, the two PMOS transistors are connected in the parallel connection. And in this way, this circuit works as the NAND gate. So in this case, when any one of the input goes low, then the PMOS network will get turned on. And therefore, the base of the Q1 will get connected to the VDD. So therefore, the Q1 will get turned on and at the output, we will get the VDD, that is the logic high. On the other hand, when both inputs are high, at that time, this PMOS network will get turned off while the NMOS network will be in the on condition. So therefore, it will pull down the output voltage to the logic low. So in this way, the given circuit works as the 2-input NAND gate. And similarly, we can also implement the NOR gate. So once again, here the only change is in the implementation of the CMOS logic. So we know that in the CMOS NOR gate implementation, in the pull-down network, the two NMOS transistors are connected in the parallel connection, while in the pull-up network, the two PMOS transistors are connected in the series connection. And in this way, this given circuit works as the NOR gate. So I hope through this video you understood what is BiCMOS logic, in which application it is used, and how this BiCMOS logic works. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.